So the things we have learned so far are all related to logical memory of a process. This is also called virtual memory of a process. For instance, like all the things that we have seen related to memory, stack, global variables, heap memory, everything, right? These are all related to logical memory of a process. Now, in this part, we will be looking into hardware. We'll not be going into more details of hardware. Rather, we will look into few things that are essential in order to understand memory management that we'll be looking into in the next class. Okay, so for students who have taken a computer architecture course or like microcontroller course, this material may be a repeat of what you have learned. So let's see, what does a processor do? Like processor is the main, like it's also called central processing unit, which actually executes the code that we give. So processor, it performs, it just has a, like logically we can think of it as a indefinite while loop, where in each loop it fetches an instruction, decodes the instruction. That means it understands what to do with the given instruction, and then finally it will execute the instruction, where execution means doing what the instruction says. Okay. Example of instructions are like load, store, test, branch, so on and so forth. So if you have taken any assembly language course, or if you have looked into some assembly, you can see that each assembly instruction defines the semantics, which says what processor is meant to do for each instruction, right? And processor, it just executes, like it just follows this while loop, fetching an instruction, decoding and executing. So logically, you can consider that processor has three units. One is fetching unit, the other one is decoding unit, and then we have execution unit. And instruction goes through these three units as it progresses. Okay, and every instruction, we can see that logically you'll have like this stream of every instruction goes through these three uh, stages, which is fetch, decode, and execute. So logically, if F1 is the fetching of instruction one, D1 is decoding of instruction one, E1 is execution of instruction one, so on and so forth for instructions two, like F2, D2, E2. Okay. And in processors, actually, what happens is we use a principle called pipelining, where you can imagine that when you have three units, there could be multiple instructions that are inside the processor. So logically, let's say we have three instructions that needs to be executed, and they go through three stages. Okay, fetch, decode, and execute. Okay, and so at each clock cycle, instruction moves through three stages. So in the pipeline, like if you look at the clock cycle simulation and inside the processor, you can see that there could be several instructions at different stages of the execution. So you can see that, for instance, instruction one could be in execution stage, instruction two could be decoding, whereas instruction three could be in fetching block. And so in order to ensure smooth pipelining, it's really important that we don't instructions don't use the same unit at the same time. So we don't want to have multiple instructions in the execution unit, right? So when we have all the units occupied by different instructions and there is no multiple instructions which are occupied by in a single unit, that's the condition for smooth pipelining. And let's look at what happens during the execution of an instruction. For instance, let's look at load instruction. Okay, what happens during execution of load instruction? So as you know, load instruction just reads from memory and puts the value that we read from the memory into the given register. Specifically, in this case, we will read from address Y and will put the value into register 0. What is memory? So memory is just slots that hold values, and each slot has a number which we call an address. And you can access memory by using store or load, which also translates to reading and writing. Okay, and you can put anything into the memory. Basically, there is no intrinsic meaning to the value that is stored in the memory. Rather, uh, the interpretation of the value depends on the program that has stored the value. For instance, value could be an address, or it could be an integer, or it could be a pointer, or it could be a function pointer. We don't know. It's memory doesn't know, whereas program knows the interpretation of the value. Okay. And an important part of memory access is cache. So cache is basically another uh, kind of memory which is closer to the processor, and it enables fast access to the memory. So memory is usually far away from the processor. So in order to uh, have faster access to frequently accessed memory locations, there is a small unit of memory called cache, which is closer to the processor. And accesses to the cache are usually way faster than accesses to the memory. Okay. And cache accesses are transparent to the program. That means program, there is no direct way for the program to know whether memory content came from cache or memory content came from actual main memory. Okay, like a content of an address came from cache or it came from main memory, program cannot know directly. Okay, and this is what we mean by transparent. So this is cache is maintained by hardware without any intervention by the program or by the operating system. And similar to cache, there are various levels of cache. Like, so we have main memory, which is the location where all the contents are stored, and there are different levels of caches. Like there is L1 cache, L2 cache, and there is also another special cache called TLB, which stands for translation look aside buffer, which is actually cache for page tables. We don't need to worry about TLB right now. We'll be looking into TLB in the later classes. And when we execute the instruction load, like R1 from load content of memory X to R1, we hope that the content of X is actually in L1 cache, because that's the fastest memory that CPU can access, right? So we hope, like most of the times when we are executing the instructions, we hope that all the memory accesses that we do are satisfied by the cache. So very few memory operations go to the main memory, because accessing from main memory is way slower than accesses from cache. And there are other important components in this memory hierarchy called registers. So registers are inside a processor. So they are just locations, or basically they are local storage units. So they have fixed width, and all the registers, each register has usually names, and they are just local slots to hold information. Okay. And why do we need registers? Because similar to caches are like, it's a fixed memory, whereas it's a faster memory, it's expensive. Similar to that, like registers is on chip memory. Registers are like inside the processor, and they allow fast accesses, and they also enable processor to avoid fetching from memory always, right? So as we saw, for instance, in the load instruction, we actually read the value from memory X and stored into register R1. So in this way, we will avoid all the future references to address X. So now, in order to access the value at address X, we don't need to do load instruction anymore, because once we load the value into R1, we can just use the register R1 instead of actually going to L1 cache or memory to access uh, address X. So that's why registers allow like even more faster access to memory contents. And registers also allows us to store temporary values that don't need to be actually stored into memory. For instance, here, let's say we compute value of some arithmetic expression, and then we store into variable E, and let's say later we use E. Let's say we don't have to store the value of E into memory, right? So in that case, registers provide a perfect way or like perfect place where you can store the values without actually going into memory. And allocating registers for a given program, like the best possible allocation for a given program, it's actually NP complete. Uh, what uh, what it means is it's non-polynomial time algorithm. It's hard. So what most of the compilers, what they do while assigning registers is there are very many register allocation algorithms such as coloring, register coloring, that they use to allocate registers to programs. So what is a program? So we saw program is just sequence of instructions, right? And each program has code that has sequence of instructions, and the code is usually divided into functions. We have main function, that is the entry point of the program, and we have various functions and subroutines, and which could actually call library functions such as printf or read. And program also contains data. So program accesses data. The data could be either static variables or global variables, or it could be dynamically allocated using malloc, or the data could be parameters, okay, or local variables. What is a process? As we saw in lecture 3, so process is an active version of the program. So sorry. So when we actually instantiate the program, that's when it becomes process. So process, as you can see, that process contains program along with associated memory, active memory, and then execution state. So here, process has various memory, like code, data, heap, and stack. This is like various memory regions that a process has. And then the execution state of process is indicated by registers and PC, which stands for program control. So the conversion of program to process is just allocation of memory. So everything that program has becomes memory. So there are various ranges of memory in a process that are used for different purposes. For instance, text segment of a process is used to store program instructions, and data segment is used to store global variables. Stack segment is used to store local variables and parameters. Similarly, there is heap segment, or like heap region of the memory, which is used to store dynamically allocated memory, such as malloc and calloc. So an important thing about processes and how process handles function calls is by using stack. So stack, like if you have taken data structure course, you know that stack is a data structure which allows last in first out access to the contents. So basically you can push onto the stack, and when you pop, it's the last element that you pushed, you get to access. Okay, examples where we use stack is like DFS, depth first search traversal. If you have written graph traversal algorithm, you would know that we use stack to store nodes in a depth first search algorithm. And also another place where we use stack is procedure calls, like function calls that we do in a process. So when program or a process does a function call, so there are things that a function call needs, right? Like a function needs local variables that are passed by the caller. And then it also needs space for local variables that that it uses to store local computations. Okay. And there are various temporary expressions that the function computes. For instance, here in this case, as we can see, the function loop, it computes the value of expression a plus b and then c plus d. So these are, you can imagine, these are like temporary variables that the function creates, but there are no explicit variables that are declared by that function. Okay. And the way function calls are handled is by using what we call stack frames. These are also called activation records. So where each frame is a region of memory which has local variables that are needed for that function. And it also contains parameters that are passed to that function. And also the return address, basically the place where the function should return after executing all the code inside that function. And the stack frame also contains space for certain temporary variables that are not necessarily declared. And the size of stack frame, like the size of region of stack frame, depends on the function. Like each function, depending on the number of local variables it has, number of parameters it accepts, the size of stack frame might be different. And the way stack frames gets organized and the way functions get functions use stack frames is as shown on the slide. So here in main, when we call bar, so a new stack frame gets created onto the stack, which contains all the contents of the bar, and it also has a return address that actually points to the next instruction of the bar. That says that after bar finishes its execution, it should return to the next instruction of the bar call in main. Similarly, inside the bar, we could have a call to foo, and then that will also create a new stack frame. Okay. Now, when the process is executing foo, when the foo returns, it actually returns to bar, and now when bar returns, it actually returns to main. And the way this is handled is by using stack frames. So stack, since it allows last in first out data access, it provides a natural way to handle function calls. So that's why we use stack frames to handle function calls. And as with all the other aspects of process, stack is just memory. So it's defined by the combination of like both compiler, operating system, and the programmer, because the way stack is organized depends on the compiler, and also the parameters, whether they are pushed onto the stack or they are passed through registers. That also depends on what we call calling convention. And the OS manages stack by just allocating a fixed size of memory in the process address space for stack. And then it just uses the memory. Basically, there is a global stack pointer that keeps on decrementing. Uh, the reason why we call decrementing is because stack grows downwards. So you don't need to understand by this what I mean by stack grows downwards. Ignore that. What you need to understand is there is a fixed memory region that is allocated for stack, and whenever function call happens, we actually push a new activation record onto the stack, and when a function returns, we just pop an activation record out of the stack. And in order to handle maximum stack size, uh, we don't uh, we don't actually dynamically resize the stack. Rather, we fix certain memory region to be stack region in the process. So that way, uh, we don't need to we can like program like process or operating system kind of sidesteps managing the stack, because it just allocates a fixed set of memory in the process address space as stack, and the stack pointer indicates the top of the stack. That way we can handle pushing onto the stack and popping from the stack. So how does memory looks like from process perspective? So process actually sees memory in terms of regions, right? So the process view of memory is called logical view, and it is also called logical memory or virtual memory. So process sees like code, data, and stack and heap. These are the different regions of memory. And these are all just logical regions of memory that make sense only for the process. Okay? And there are few of these code regions that grow, few of the code regions are fixed. For instance, code is fixed. Code and data segment are fixed, whereas stack grows and shrinks, right? Because based on the function calls that are currently active in the process, stack grows and shrinks. Similarly, heap can grow and shrink. And the other aspect of memory is the physical memory. That means the actual memory that we have on the system. And this is whole another problem. And the way physical memory is managed by the operating system is whole new area of study. And in the next class, we'll be looking into memory management, where basically we'll be looking at how logical memory is organized by an operating system. Basically, how a process sees its logical memory and how this logical memory gets mapped onto the physical memory that's actually available on the system. And the way this works is so when you actually compile a given program, our compiler converts the C code into an object file, okay, object code, and then linker links all the object files into an executable, and then loader loads the executable into memory, and then operating system takes care of memory management, and then finally instruction execution happens at the architecture level, where processor just fetches each instruction from the program code and it executes it. Okay. And in the next class, we'll be looking at how compiler puts all the code that we write into object files and how linker organizes them into an executable. And finally, how operating system, given an executable, how operating system allocates memory for that executable. Okay. Thank you.